Okay, so welcome to the class. We're recording right now. So let me share the slides with you. Okay, hold on a second. Just a second. In the meantime, my slides changed position. Okay, once more. Sure. Okay, now. Okay. Does everybody see my slides right now? Okay. Yes. Okay, great. All right. Thank you so much. Okay, so that's where we were last time. You know, just testing whether one understands what a power set is of a set, and these kind of complicated like testing cases, like to just distinguish what does it mean to be an element and what does it mean to be a subset. And you know, tricky questions involving singletons, which you should distinguish from elements in these singletons. What about empty sets, etc. Okay. Okay. So moving on. Sets are unordered objects, right? So they are collections of objects of some elements, which are where order doesn't matter. But very often in computer science, we have in programming and in other aspects of life, we're dealing with ordered elements. So for example, ordered pair. And we designate ordered basically sequences, okay, that's the caper to the story, with open and close round bracket, as opposed to the curly bracket with designated sets. So open, close round bracket A comma B is an ordered pair. And because it's ordered, so if I define an ordered pair with A first, B second, that's a different pair than the ordered pair that has B first and A second. Whereas if I define a set which contains elements A, B, I can define it like left-hand side here or right-hand side here, and I will define the same thing because these are equivalent sets because they have the same elements. A is an element of both, B is an element of both, and nothing else. But this is not just, this is a special case of sequence with two elements. You can have three elements in a sequence. So that would be a triplet, right? Where it's again ordered. And it matters the positions I write these things in. Or a four tuple. In general, you can have an N-tuple, N element sequence, and you just write them with commas, okay? Soon we'll see that there is a way to define sequences where I don't have to list them all. I can define them through some formula, sort of similarly to how I define sets using a set builder notation. So I don't have to list elements, and especially if I cannot do that for infinite sets. Likewise, we'll have a case of infinite sequences because sequence might not stop anywhere. So it might be defined for all integers. The notion of a sequence is closely related to Cartesian product of sets. So consider two sets, S and T. And a Cartesian product of S and T denoted this way. So it's S and this kind of multiplication sign, T. And that's read Cartesian product of sets S and T if you know that S and T are sets. And the Cartesian product is defined as the set. Here is the case of a set builder notation. It's a set of elements of the form open bracket S comma T close bracket. What is this? It's a sequence of length 2. In other words, it's a pair. It's an ordered pair. So this set which is defined using the set builder notation, is a set of pairs. ST such that the first element in every pair must be an element of set S, and the second element of every pair must be an element of set T. So this is a set builder notation. Here is some function of some elements. I take element S and I take element T, and the function is kind of hard to see, but it is a function. I take two elements and I make a sequence out of them, such that some Boolean condition is met, namely some constraint, some predicate on variables participating in this stuff is met. So somebody says, is S cross T the same as T cross S? No, right? Precisely because these sequences are ordered. But there is a special case where they are equal. If S equal T, then yes. Okay, so for example, take S and a set of three elements, A, B, C, and T a set of two elements, 1, 2. Okay, so S is a set of three letters, T is a set of two integers. Here is an explicit listing of all elements in the Cartesian product of S and T, right? It's all pairs of the form, first element is one of these, the second element is one of these, right? So by the way, how big is the Cartesian product here? It's this times how many are here, right? Because for every choice here, you have a choice here. So you have what cardinality of S choices and cardinality of T choices for the second element. And each pair is an element of the Cartesian product. Okay, let's take some examples. So actually, some more notation. What if I take a Cartesian product of a set with itself? That's an example I just sent on the chat. If you take a Cartesian product of a set with itself, that has a special notation. If you think of this as a multiplication of some form, then we can denote this with exponentiation. It's a set cross multiplied by itself. So for the case of this set, here would be its Cartesian product with itself, right? You can ask, just to test yourself, is set T a subset of T squared? Well, no, right? Because T is syntactically contains integers. So all elements of T are integers, and all elements of T squared are pairs of integers. And an integer and a pair of integer are different objects, right? So what is R squared, right? So remember, R is the real numbers. Okay, so pairs of real numbers. So if I want to say that my code, takes inputs which are pairs of real numbers, I would just say X, the input, must be in R squared. Okay, that would be a condition on some piece of code. Okay, or if I want to say, right, so it's a kind of notation that is very useful. It allows you to succinctly express where, what, let's say, a piece of code operates on. Yeah, what are its input outputs domains? Z square, right, where Z is a set of integers, so the Z square would denote pair of integers. Let's have another example. I have three sets. A set of drink is a set of with just two choices, orange juice and coffee. The main dish is a set of waffles, eggs, and pancakes. It's some sort of breakfast place. and a side is either hash browns or toast. Now, a breakfast selection is a set that is a cross product of set of drinks, set of main dishes, and set of side dishes. So an element in breakfast selection is a triple because this cross product is contains triples. The triple, it would be, so for example, this triple is in it. Orange juice, because it's an element of drink, eggs, because it's element of main, toast, because it's an element of side, right? More generally, if you have some sets A1 to AN, here the example was, this was A1, this was A2, this was A3, then I can take cross products of A1 with A2 with dot AN. What will it be? It will be a set of sequences of length n such that the ith element in the sequence, call it xi, has to be an element of set AI, of the corresponding set at this index, right? So simply first element of the sequences must be in A1, second element of sequences in A2, etc., right? And this has to work for every index. This is again a set builder notation, right? A function of some elements, namely I take n arguments, I call them x1 to xn, and I form a sequence out of them. And here I say such set and a bunch of constraints on these elements. And the constraint is that for every index between 1 and n, the corresponding variable here, the ith variable must be an element in the ith set. So basically, you can think of cross products as records. If you have seen that in some computer language, a record, right, is a field where I say perhaps it has n fields, and the first field is an integer. That would be A1 would be an integer set. The second field is a bit. So A2 would be just 0 and 1. The third field is an alphanumeric expression, okay? And on, right? So that's exactly what this corresponds to. So this is it's an abstraction of records, if you will. But it has other uses. If I can now take an nth power of a set and using the same thing as before, right? I say, okay, what's an nth cross product of a set with itself? These are all sequences whose elements are simply members of S. But these sequences are of length n, and this is designated here. So instead of saying inputs of my code are sequences of elements such that every element is an integer, I just say the inputs are in z to the n. Okay, and that's it. That suffices. That's a fast way to say it, right? Here is, okay, what is this set? So it's a Cartesian product of 3 times of this set with itself, right? But it's a set of bits. It is just 0 and 1. This is just triples of bits or sequences of 3 bits. This is the same, right? Because sequences of 3 is a triple. So that's a notation that we'll use all the time because we want to say, the input has to be an 8-bit string. So you just say that the input is in this set to the 8th. R4 is 4 tuples of reals, right? By the same logic. Here is some notational issue. if it's because in computer science we often deal with strings, right? Like it's a natural object, bit string, string of characters, right? Manipulations of strings it often comes up. So we want to say, well, okay, these are strings, but what are the characters in the string? What are they? Perhaps they are digits. Perhaps they are bits. Perhaps they are ASCII symbol. Perhaps they are letters in the English alphabet, and on, right? So in these applications, I will very often basically think of the domain where the characters live as an alphabet. It's a natural thing. I want to say, you know, here is a string, a Latin word. Well, it's a string where every character is a member of a Latin alphabet. Here is an English string of English text. Every character is a member of an English alphabet, etc. So, in that sense, we'll say binary alphabet, meaning bits, or a decimal alphabet, meaning decimal numbers, right? From 0 to, you know, in the Arabic numerical notation, from 0 to 9. So if sigma stands for the set of characters, basically in your alphabet, then sigma to the n is a set of strings of length n, such that every element in the string is a member of sigma. In other words, sigma to the n are n long words in this alphabet sigma. And okay, let's take, and I can denote them in two different ways. If let's take a sigma that is a primitive alphabet that has only two signs, A and B. So here is a notation of a sequence in sigma 4, right? For tuple, every element in the tuple is an element in this alphabet set. But it's kind of annoying to define, you know, if I wanted to define strings in this way, then a string that says elements, I would have to denote as E, L, E, M, N, right? Pretty annoying. Like the natural way would be just to say elements. Indeed, I can denote this sequence simply as in this way, like a faster way. So this way makes it somehow basically casts an element of this set as a sequence. And this way casts it as a string of length n. We will say that this is just a different notation for the same object. Okay. Now, why would you ever use a punctuation if you can denote things fast in this way? Well, here is the thing. What if the underlying set is not a set of single characters? So elements of sigma, so for example, think of hex, elements of sigma are not single characters. So that happens with some languages, right? That a character, okay, well, I can still talk about like expressing stuff using these elements, even though some elements might not be made of a single character. And then this notation is ambiguous. Let's say that I had a sigma contained A, B, and then an element which was itself a concatenation of A, B. So it was just a AB little sequence. Well, then this is not clear what that stands for, right? Because maybe it's a AB, comma, AB. Or maybe it's A, comma, B, comma, A, comma, B. So this notation disambiguates that. But it's only relevant if underlying set has this property, and that's like, you know, not a property of most alphabets. So okay, so 0, 1, 2, 3, right, in my alphabet is made of bits. Then these are sequences of 3 bits, but I can equivalently denote them as strings of length 3, which are bit strings, right? And now you see like how, you know, how useful this notation would be to describe computer objects that come up in computer science. An important operation on strings is concatenation. So let's say a string X is abba. Okay, so it's a 4-character string over this alphabet that contains A and B. Another string is bab. Okay, it's a 3-character string. I can concatenate 2 strings, X and Y, and write it as XY. And if X equals abba and Y equals bab, then this denotes a string formed in this way. Okay. Now, when you are told that, you know, here, my input is XY, how do you know it's a concatenation? Well, you kind of don't. But if it's said that X is a string and Y is a string, then you know that XY stands for concatenation. Unfortunately, we put variables together in some other notational context. Like, for example, if X is a numerical value and Y is also a numerical value, natural, integer, rational, real, XY would stand for multiplication, right? It's a common notation. So you have to go by context. If these things are numerical variables, you know this is multiplication. If they are string variables or sequences, then putting them together like that stands for concatenation, conjoining 2 sequences, building a longer sequence by taking one as a prefix and the other as a postfix and putting them together. You can concatenate in this way with a single character. So A is a character, but it's also a string. It's a string that contains a single character. Now I'm moving levels and violating basically, you know, boundaries, type boundaries, because I said, well, a set that contains a single thing is not the same as that thing. A sequence that contains a single thing is also not the same as that thing. So this is basically an abuse of notation. Okay, I'm going to, but okay, like you have to get used to it because that's what people do. They say if they want to concatenate a string with a character, they're gonna say XA, and XA is going, you have to know that it's going to resolve in this string if X is this string. So, you know, don't blame me. It is moving across sort of abstraction layers, whether we think of this as a string, which is a sequence of elements, and it contains only one, or we think of this as that element, you know, nothing we can do about it because, you know, however upset you might feel, this is how people use this stuff. And a concatenation of X and Y can be denoted using this, you know, just list them one after another. Or if you want to stress that what you mean is concatenation, precisely so that to avoid somebody thinking, okay, what if these are integers? And often in code, this kind of stuff happens, right? Like perhaps these things were integers at some point, but they were cast as strings of numerical digits. And do you mean here that I actually take the numerical values and multiply them? Or do you mean that I take their digital representations and concatenate them, right? If you use this notation, it is ambiguous. What do you mean here? There is a special symbol, like for an empty set, for an empty string. It's a string that contains no elements, different from a set that contains no element, although that's like, don't ask me what the difference exactly is. They're just a different class of objects. But now that I say it, I'm not exactly sure how I would go about explaining the difference between an empty set and an empty string to anyone. We can take it on Piazza. So an empty string has a special notation. It's a lambda, a Greek letter. X lambda stands for concatenation of X with an empty string, but that's just X, right? Because concatenating with the lambda, which is empty, just meant that you have not increased the size of this sequence. You added nothing to it. It's just X. And if you prepend X with an empty string, you also don't change the result. We have a special notation for a length of a string, and it's denoted with the vertical bars. So if you know that X is a string, then vertical bars with X in it denotes the length, which means number of characters, right? So if a string is in sigma 4, then you don't need to look at the string. Its length is 4. If a string is in this set, it doesn't matter what string it is, it has length 3, etc. Now, here is, just to upset you further, just kind of, yeah, whatever. It's kind of a joke, but it's not a joke, right? It's maybe kind of interesting to put it together. So by now we have 3 ways of using this symbol. And there's more, actually. So first of all, we said that if X is a set, then vertical bars around X stand for the cardinality of a set. We also said that if X and Y are strings, then right here, putting a vertical bar between them denotes concatenation. And now we say that if X is a string, then this thing is its length. Okay. I cannot do anything about it. It is ambiguous. Sometimes in some weird cases, you better be aware of this so that when you want to say something that could be thought of ambiguous, somehow false, could be interpreted in this way, then be sure to disambiguate it, right? If you write this, make sure that X is a set and that it's clear to the reader that X is a set, right? Or that X is a string. Okay. One more thing about sequences. I can basically denote infinite length sequences over some alphabet. So before I didn't define what the sigma to the n is, right? Sigma to the n was a set of strings whose length was n, and all the elements in the string were elements of alphabet sigma. I have a notation for an infinite. Okay, this is actually sorry. This is not just infinite. No. Okay, no, scratch it. Okay, it is infinite, but all right. Okay. Sorry. I didn't say this correctly. This is a notation for all strings over alphabet sigma. There is infinitely many of them. and the set is infinite. But actually every member of this set has a finite length. So at some point I said infinite sequences, and that was not true. Yeah. So I misspoke. This set is defined as a union of sigma to the 0, sigma to the 1, sigma to the 2, sigma, etc. So you could use a union that goes from I equals 0 to infinity over sigma to the I. So that would be a faster and more succinct notation for this. Okay. What is sigma to the 0? It's an empty string. If you look at the definition of what a Cartesian product, if you sigma to the n is strings of length n, where every character is in sigma. Sigma of length 0 to the 0 is the strings of length 0. There is only one such string. It's an empty string. 0 and 1. So take a binary alphabet. Sigma is a set of two elements, 0 and 1. Then 0 and 1 are both members of this set. 0, 0, 0, 1, 1, 0, 1, 1 are members of this set. And what will follow will be all bit triples, and then all bit 4 tuples, and so forth. So in other words, this denotes all binary strings, including an empty one. So if you want to say, my input is a binary string, but it's unconstrained of how long, it's a pointer to, a buffer, and it can go arbitrarily long. This is the way to say it. Okay, this expresses all strings over this alphabet, no matter what their length. But each such string is still finite sized, right? But any size is okay. It will eventually be here, right? And we have a special notation for the same thing, but just kicking out an empty string. So it's a sigma plus. It's a union, same union, except you don't admit this one. Okay, so in other words, this would be a notation for all non-empty binary strings. Okay. Yeah, so A star would be all English words indeed. Somebody says on the chat. Okay. So using the fact that the size of the Cartesian product is a multiplication of the size of the sigma in this case. So a size of Cartesian product of A and B is the size of A multiplied by the size of B. This, by the way, also explains this multiplicative notation for Cartesian products. So what's the size of sigma squared? It's the size of sigma squared. That again aligns very well with this notation, right? What's the size of sigma to the n, right? N bit strings, n length string over alphabet sigma is the length of sigma to the n. If sigma is bits, so length of sigma is 2, because there's 2 bits, then bits to the n, how many? Well, these are, what is bits to n? It's n bit strings. How many of them are there? 2 to the n, right? You have one choice. You have 2 choices for every bit. 2 choices times 2 times 2 times 2 n times 2 to the n, right? Okay, just just a remark about how, like in the end, natural these notations are. Okay, functions. So next chapter. A function is a way to map elements from one set to another. denote a function like this. F is a function. Again, we see this colon second time in a different context. It's a function from set A to set B. A is called the domain of a function. That's where the arguments of the function live. And B is the codomain, or another word is target. That's where values of the function live. So for example, this is a pictorial representation of a function, particular function, on domain consisting of A, B, C, D, and codomain existing of 1, 2, 3, 4, 5. It's a directed graph whose beginning start points are elements of the domain, end points are elements of the codomain, and for every domain element you have to have one and exactly one arrow pointing to somewhere here, and that's the only constraint. If some of these don't have an arrow, that's not a function. Because it's the function, then we would say, let's say B has no arrow. Then we would say the function is undefined on B. And therefore, it's not a function from this domain because it fails to define the value on some argument. If there is 2 arrows, it's also not a function because it fails to define the value in a non-ambiguous way. The range is a special concept, but it's quite okay if some elements of the codomain are left out. So it's still a function, even if it doesn't cover everything. Like for example, x squared is a function from reals to reals. It's okay that x squared never attains negative numbers. And also, it's okay if two arguments are mapped to the same value. In fact, x squared maps 1 and -1 to the same value. Range is a restriction of the codomain to only those elements for which there exists a pre-image under this function f. So 1 is in the range because there exists an element in the domain which maps to it. 3 is not, because there exists no element in the domain that maps to it. I can define a function as a graph, but if the domain is infinite, then that's not going to work very well. I can define it as an arithmetic formula on a numerical domain. Here are, so that's a function. I don't know offhand, cannot compute so quickly if it has collisions. So if for some x and x prime, fx is equal to fx prime. In an event, that wouldn't change the fact that this is a well-defined function. Examples of things that look like function expressions, but are not really functions, or at least not from the domain of reals to the codomain of reals. So if I say f of x is plus minus square root of x, well, first of all, square root of x is not defined for negative reals. Secondly, even for positive reals for which square root is well defined, I seem to be saying that the output is both the plus square root and the minus square root. So this violates what a function is supposed to be. So every argument has a value and has a unique value, no 2 values. 2 over x is also not a function because it's not defined for x0, okay? Here is a special property of a function that is 1-to-1. Such a function is also called injection. A function is 1-to-1 if the following predicate is satisfied. The predicate says it's a quantified formula. It says for all x and x prime which belong to the domain, you can see the special notation here where I do a universal quantification restricted for certain domain, okay, which is the domain of this function. For every x and x prime, the following implication must be true. If x and x prime differ, then the function values differ on these two arguments. This function is not one-to-one because f of b and f of d are the same value 4. So b and d will violate this implication. B is different than d, but f of b is the same f of d. So hypothesis is met, consequent fails, implication not true. This function is one-to-one, right? Because there is no two values which map to the same that would violate this. This two values that map to two arguments that map to the same value, they're called collisions in a function, right? So you might think of hash function that hashes database elements into some buckets and has a collision. Two arguments fell in the same bucket. Examples of one-to-one functions. So is squaring a one-to-one? No, because it has a collision. This is a linear function, and so it has no collisions, right? Because if you plot it on XY graph, it's a line. And it's, you know, except of horizontal line, it has only collisions. Every other line will define a one-to-one function. A function that takes a bit string of length 3 and outputs another bit string of length 3, where the function is take a bit string and replace the last bit with a 0. So take a bit string and kick out the last bit and stick a 0 in its place. Is this function one-to-one? No, because it has collisions, right? So if I take these two bit strings, they will both map to 110 because I kick out the last bit, I replace it with 0, right? What about a function that takes 3 bits, outputs 4 bits by concatenating a bit string with a 0? So for example, if I start with 101, I get 1010. That function has no collisions, right? Because adding a bit preserves all the previous ones. So if they were different from x and x prime, the output is still different. It's x with a 0 and x prime with a 0, two different strings if x and x prime differed. What about a function that takes power set of this set? In other words, any subset of this set, right? So P of A is a set of subsets of this set. And outputs an integer where the function is defined as the cardinality of this subset, right? So X is a member of the power set, if and only if X is a subset of set A. And I can assign cardinality to a set. Is that one-to-one? No, because all singletons will be mapped to the same cardinality 1, or subsets of length 2 will be mapped to 2, etc. So many collisions there. Sort of flip of this concept, although not exactly, but a very important other concept is that a function can be onto. We call such function surjection. For a function to be onto, the following universal quantified formula has to work. For every element in the target, in the codomain, there is some element in the domain which is mapped to it. That element is called pre-image. And if the function is, if the function is one-to-one, then pre-images are uniquely defined for elements in the range. If the function is one-to-one and onto, then pre-images are defined everywhere and unique too. Okay, so the function is onto if every element in the codomain has a pre-image, some pre-image. This guy has 2, this guy has 2 pre-images, but this guy has none. So this function is not onto. This function is onto, right? So every element here has some preimage. This has actually a set of preimages. That's fine. The function is onto if it covers all the codomain. If if all the codomains are hit by the function. Let's check. Is x squared onto? No, because negative numbers are never outputs. Is a linear function onto? Yes. What? Oh, haha. Sorry, forgot that I defined this here for domain integers. And for domain integers, it's not onto. Take integer 2. It's never an output like this. So 2 is not 2x plus 3 for any x. Yeah, because what would this x be? Minus half, right? And that's not in the domain. However, if I change the same numerical expression of the function and I think of it as a function from reals to reals, then it's a line and it's, okay, onto, right? Let's look at this one. From bits to bits, the same function, replace the last bit. It's not onto. It will never output a string that ends with a 1. Okay. What about this function? Take 3 bits, output 2 bits by dropping the last bit. It's onto. Every bit string has some preimage. In fact, it has 2 preimages. That bit string with a 0 and that bit string with a 1. They both would be mapped to the bit string 1, 0. What about take a bit string, output the same length bit string by remove the last bit and concatenate it at the beginning. So in other words, rotate. Take the bits, move them to the right, and because one fell off, stick it to the beginning, right? Because it's a rotation, so intuitively you're not losing information. So it should be that everything. Why is it an onto? How is it that everybody is mapped by a rotation? We'll take an inverse rotation, rotate it back. You can do it, and you invert this function, right? So this is a quick proof that the function is onto. Well, this relates to a concept of bijection, that the function is a bijection if it's both one-to-one and onto. And if a function is a bijection, if it's both one-to-one and onto, then preimages for every element, if the function maps from domain to some codomain, if it's one-to-one, if it's onto, then every element in codomain is hit by someone. But it's one-to-one. So every element in the codomain is hit by one element only. So therefore, take an element of codomain, and if you look at preimage, it must exist. Some preimages must exist by the onto property, and they are unique by the one-to-one property. Therefore, such function is invertible. The bijection can be inverted back. And one thing that immediately follows from the notion of a bijection is that the only way it can be a bijection is if the number of elements in the target is the same as elements in the domain. And also that it has an inverse, right? So an inverse of a function from a domain to target exists and is denoted f2 minus 1, like inverse of an integer, but it's not integer, right? It exists even only if this function is a bijection, and it's a function, the inverse is a function that takes the codomain and maps it back to the domain and satisfies the following property. Whenever, for every xy, if f of x is y, then f of inverse on y is x. This is a definition of f inverse. It's a function that takes an element, and what's its value? The value is an x such that f of x equals y, x in the domain of this function. So inverses exist only if the functions are bijections. And this is what I just said already.
Just a heads up, it's after 12:50.
Yeah, and that's my slides. So let's stop